Hi, this is STEMDIT Podcast, Innovation at the Edge with Open Source. Today, we get to learn from an early RISC-v adopter who has shipped RISC-v based products, so we'll know a lot more about those. We are with Ted Speers. He's a technical fellow at Microchip Technology, where he's responsible for defining roadmaps for low power, secure, and reliable FPGAs and SOCs, and he significantly contributed to advancing Microchip's portfolio in the field, particularly with products like PolarFire SOC. Ted also serves on the board of directors of RISC-v Foundation, so we'll have a lot about RISC-v today. How are you, Ted?
Great, Kim. Cliff, nice to meet you guys. And I guess I've met you before, Kim, but really appreciate the opportunity here.
Cool.
First podcast I've ever done, so hopefully your audience appreciates it. Or I do good. I do well by your audience.
Yeah. How are you doing, Cliff, today?
Yeah, pretty well. Thank you.
Very good. So, Ted, so tell us a little bit about yourself, your career. Where, what brought you here today? What you do today?
So it's pretty unusual background in the sense that I was born in Saudi Arabia. My dad worked for the Arabian American Oil Company, known as Aramco. And then even he was born in, was then India, is now Pakistan. His dad was a professor at Foreman Christian College in Pakistan. So that background is pretty different. Then, I went to elementary school, junior high in Saudi Arabia. Parents moved to Texas for high school. I then went to Cornell and I studied chemical engineering. The big plan was to get into the oil industry, just like my dad. Well, he wasn't a chemical engineer. He had a PhD in Arabic ultimately, but I was an engineer, and but so I figured I'd get into the go-go oil industry. And when I graduated from Cornell with a chemical engineering degree in 1983, that was when the oil industry completely tanked, and the whole chemical industry tanked as well. It's kind of interesting. So I was living high school in Houston, and in the early 80s, when kind of Japan basically killed Detroit, and there was no U-Hauls in Michigan, and there's over a glut of U-Hauls in Texas. And then about when I graduated from Cornell, there was no U-Hauls in Texas. They'd all gone back to Michigan. So it was actually a horrible event for anyone connected with oil economy at that time, or chemical. It was a big depression for that industry. So as it happens, my girlfriend, now wife, was going to get her master's at Berkeley in chemical engineering. So I came out here and started looking for work, and realized that chemical engineering kind of is applied to making of chips. In Silicon Valley, there was actually they actually made chips back then. And so I got a job. I kind of read about how you make chips, and got a job at LSI Logic in 1984 finally, in a fab. So I was an etch engineer. So I was etching the silicon wafers to make pattern metal lines and stuff like that. Then 1987, someone here at Actel at the time, was a startup, came from LSI. They called me and got a job for me at Actel in a fab as well. So we had a process called anti-fuse, where you take two wires and create a voltage across a wire and blow a fuse and make it a conductor. And that's created an FPGA technology out of antifuse. We use Data General as their factory to run the production, or the call it prototype research lots. But immediately we're starting to say, well, we can't make the chips here. Let's go to foundries. And so this is before TSMC existed. We made a deal with Matsushita. They made wafers at the time, and also TI. So my job, making wafers was going to end because we were basically losing our fab, and other people were going to make it. And I kind of, I'd like to say, I mutated into an electrical engineer at some point in there. And there was some big disaster with our product. It's kind of, we're a startup, and it's kind of all hands on deck situation. And I'd been reading about the architecture of our chip. There's pretty good documentation about it. So I didn't, I came in here, I didn't know what a flip-flop was. I didn't know, basic things when I started. But I, became an expert, kind of a FPGA whisperer. I could figure out what was going on inside the chip when there was problems. So I was a product engineer for a while. And then at some point I moved over to what's called product planning, which is where you define your FPGA roadmap. And I've been doing that for a long time in this product planning. I think I moved into product planning in 1996, and I've been running the organization more or less from 2000. So as I got into the FPGA business, kind of a long story. Did a lot of we're always, Actel, always not the two big guys to Goliath were Xilinx and Altera. And so even though Actel invented the term FPGA, that's probably a little known fact. We coined that term. We never got to. We couldn't keep up with the big guys, I would say, but we always had very differentiating technology. So we were always profitable, but the growth was hindered by a couple of factors. I think it had to do with our technology choices. I remember we used to have these meetings, or weekly, drinks and appetizers and stuff. And we were talking with the CEO at the time, John East, and some other people, and we kind of made fun of Xilinx and said, "Oh, their part's a kludge and our part's much better." And John said, "Well, their part's a kludge on the outside. It was difficult to place and route it as Xilinx FPGA at the time, but our part is a kludge on the inside. There's all kinds of high voltages that have to get routed to the FPGA. It was a special process, and making that antifuse blow was very difficult." And that was, it's like something about one of my superpowers, actually, though, and John actually had it too, is cognitive dissonance. When you hear something that kind of violates the way you're thinking, a lot of people ignore it, but I'm like, I latch onto it. And I think it's difficult to it was difficult to follow Moore's law like Xilinx and Altera were able to do. So they were able to get on the wave, surf on the communications market. So they basically, the FPGA the universe has an age of inflation. The FPGA age of inflation happened in the comms market, where Cisco and all these people, and we were a big comms customer, but couldn't keep up. And eventually, even though the SRAM was fundamentally harder technology to build an FPGA out of, just following Moore's law, and it was, I think those two win the mainstream FPGA market, let's call it. But we had
so the Actel were flash based. Is that the difference?
Originally, they were not. They were anti-fuse based.
Okay. Yeah.
So anti-fuse is non-volatile, and this is the biggest problem: is one-time programmable.
Yeah.
So you programmed it, and if it didn't work, you had to throw it away. And so that was so it was difficult. Like imagine soldering it on. You can't change. If you find a mistake on your board, you can't change it anymore.
Mm-hmm.
This is an example again. Give John a credit again. It's like so we had these differentiators. We were non-volatile, was appreciated. We were rad tolerant. We were low power. We were secure. But this company called Gatefield that had the flash-based technology. So flash was all of that and reprogrammable. So that was micro. We switched. We bought that company Gatefield, and we started switching over to flash. 2000-ish, I would say. But John had a lot of resistance to that too. Everyone loved the internal technology, and John said we need the reprogrammability. So that was, I think, strategically important, and but still, flash just doesn't keep up with the pace of Moore's law. So we're just always battling that a little bit. But again, very profitable throughout, and enjoyed a lot of growth actually recently. So
yeah,
I think we believe we're the number one growing FPGA company in the last several years. But
it's very interesting because I worked at Telzon years ago, and back in the late 90s, and we use Actel FPGAs. Some of
the flash ones or the
the anti-fuse. So I remember programming those and putting them on boards. So
yeah, they were by far the fastest FPGA. Was no contest, and densest FPGAs for a while. So we could do stuff no one else could do, and much more logic, much easier to place and route. But again, literally, I think it's just Moore's law. You can't just things get better. It's kind of a lesson people have. It's a lesson from we can talk about books and stuff. Innovator's dilemma is the incumbent technology, or a technology just gets better over time, and so you got to watch. You don't worry about where it is today. Is much important. Today it'll get some niche, but then it'll ultimately take over. So we were definitely better than an SRAM for all those key FPGA features for a while, except for they could reprogram, and so eventually they became as big as us, as fast as us. So, but not as low power or secure as us. So we've still got that.
Yeah. So the Microchip FPGAs, are they still flash based?
Yeah. So So we switched to flash, and it's the actual technology on the current node, 28 nanometers, is Sonos based, which is it's similar to flash. It's different, but it has all the same benefits. And we've been talked about our next node. It's going to have all the same benefits that we have with the current node, but it's not announced yet.
Yeah. So to understand that, so these are flash cells at the logic level, not in some separate RAM that gets loaded in at startup.
Yeah,
Is that right?
that's a big difference, big distinction. Yeah, so there's people. I call it flash on the side. So CPLD market. If you get a Lattice or an Altera CPLD Max 10 or Mac XO, there's an SRAM FPGA in there, and there's a little bit of flash memory in there as well. And so you program that flash memory, and then when you power up the part, it'll load the SRAM, but then you turn the power off again, that goes away. So you basically have, in a way, the worst of both worlds, but it's got some benefits. It's good in the sense that it's kind of two unique technologies, but they're well understood. And what we do is we call it an embedded flash FPGA fabric. So the actual switch inside the FPGA fabric is a flash or non-volatile memory element. So we program when we program that flash cell, we're actually overdriving it, putting more electrons on it. So it then it's used to control the switch or the pass gate that's used to connect all the routing up. So so it's a special use of flash technology, but again, it has benefits. When you do an architecture that way, you get we can talk about it. Real very low static power, high performance on the switch, and it's also beneficial for security in the sense that data isn't moving from a SRAM into the FPGA fabric that's easily probed out. So it's hard to you can't tell what's been programmed into the FPGA.
So one issue we've dealt with in the past is, like, if you put a device in a power switching device where there's lots of EMI, like a traditional FPGA, if you flip a bit in an SRAM, that you're basically corrupted, or it's going to act differently now. But I assume a flash-based FPGA, if you took an EMI hit or some, I assume it would still keep operating the same way.
Yeah, shame on me. I just mentioned it before, but that's like that's the biggest value add of our technology. It's the switch is SEU immune, so it does not. An AND gate is always an AND gate. An input is always an input. An output is always an output. And so you get these effects. An SRAM FPGA, even at sea level, there's a failure rate because of neutrons in the atmosphere, or used to be alpha particles inside the package, but it's atmospheric neutrons will cause an FPGA switch to flip states, and so you can create shorts and opens, and AND gates become OR gates, and they have so those companies cope with it by building those are all scrubbed, where there's circuitry in the background that ultimately figures out that, okay, I got one of these things, it's bad now, and it'll go fix it by itself. But there's that time period where the chip has been operating, where that bit has been flipped, and so now, depending on your system, you have varying degrees of tolerating it. But the fit rate of those flips, are totally measurable at sea level, very measurable in airplanes, and just overwhelming as soon as you get into a space environment. But as a result, and I showed, any airplane that you fly, you get on, maybe news to you, but I fly airplanes all the time. It just reached 1 million miles. Got hundreds, if not thousands, of our FPGAs on there just for that, because the bits that they don't switch. The AND gates stay AND gates. And then yes, so airplanes filled with our FPGA technology, and then I think this will be a big part of our talk. But this, we've been in space. Our FPGAs have been in space starting in the early 90s. They figured out the antifuses had this property where they didn't switch, and so we've been to the Cassini mission to Saturn, the New Horizons mission to Pluto. All got our FPGAs on it, which is very cool.
Yeah, that's very interesting. Yeah, fascinating.
So let's move towards the generational changes that I think you've been long enough witnessing this. So probably you've designed multiple generations of these products, and so you made a switch to RISC-v in your polar fire SOCs. And so what was the driving force behind that?
All right, so a lot of things. One is that I'm a little bit crazy, but so we, I'm going to say things about ARM, but ARM's a great company. ARM, so I'm not going to say I have nothing really bad at it. ARM enabled a whole industry that wouldn't, enabled the cell phone industry. So obviously a great company, but being that, they started, obviously focusing on, Qualcomm and the people that are buying these type of cells. And for years, we knew we needed Linux, but we also, wanted to meet some of the needs of our high reliability customer base. And, ARM had the M3 line. We were actually the first, not the first FPGA with ARM, but my product called Smart Fusion is the first FPGA. I call it the de facto SOC FPGA architecture. So we're the first company to integrate an ARM with an FPGA, connecting the two with an AXI bus. So that was a product called Smart Fusion. We did that. It was a Cortex M3 with Smart Fusion. But we wanted, how do we get Linux in this market? And ARM had a product on their roadmap all the time called Kite, which was the Linux in an R class. It was going to be an R15 or something. I don't know what it was, but it was always moving out on the roadmap. We're never getting it. From ARM, and we knew. But we were right that everything was going to Linux, and what RISC-v enables you to do, and I have this kind of slide on the magic RISC-v is you don't need an architectural license to do your changes, and you can, if one vendor doesn't make it the way you like it, you can go to another vendor. And so we got. So I saw the appeal for RISC-v. I know the exact date. I heard about RISC-v and did a whole keynote about it. It was December 9th, 2014.
Wow.
Just a few years past the 11th anniversary.
Yeah.
A few days, but I saw the potentials, but we had pretty good relationship with Sci5, which is the RISC-v inventors, basically started that company. And we said, well, can we take your Linux capable product and make it so one processor can run Linux on, an arbitrary number of those quad processors, and then make the other ones operate in a real-time deterministic mode.
Mm-hmm.
So we worked with Sci5 and worked on the L2 cache architecture, so we could turn that L2 cache at the user's option into what we called a tightly integrated memory. And so one or two of those quad processors can be running not in a Linux environment where you have to go out to DRAM, but run directly from the RAM there with completely deterministic timing. So we have a slide where we got Linux. I'm trying to figure out. We got Linux running on two processors, and we got the other processor, and we measure the jitter of the interrupt response, and it's literally zero. The response is the same every time, no matter what's going on with the other processor. So, anyways, couldn't have done that with ARM, and could work with a vendor, and so so that was a big part of the sale. But there's a lot of I was definitely a zealot, so there was a lot of evangelism internally, because people are definitely afraid of switching from ARM. Is the ecosystem going to be ready? There's software is a hard thing, and so I was constantly talking to people, showing people I saw you, Kim, showing up on the email chats, all the work you were doing on the software ecosystem. There's a guy named Richard Jones at Fedora who did a famous email where I got all this 85% of the Fedora packages working on RISC-v. Another guy, Manuel, did the same thing for Debian. So showed everyone it's a Linux world. We got people working on Linux, so it's ready, and the software ecosystem is working here. So I had to convince people that the software was going to be ready, that we could do something differentiated, and you had to lower the risk of RISC-v in people's minds internally before we took that leap. But eventually able to convince people. So I was at Microsemi at the time. Microsemi did not have an incumbent ISA to support, so it was probably Microchip. Since we've joined, Microchip's been very supportive of what we're doing on RISC-v, and it would probably, the fact that I was at Microsemi helped me convince, get past some of the, had less enemy or less people.
It's not quite a big a ship to turn there at Microsemi than Microchip.
Yes. Then like I said, as soon as we got over to Microchip, they've been very supportive of our roadmap, and have I'm really proud of this, really. But not our business unit, different business unit bid and won something called HPSC, the High Performance Space Computer, something we're building for NASA, and we're testing the first silicon right now. That's a 8-core RISC-v vector processor that I think is going to it's going to do great things for the world, but definitely for Microchip and for RISC-v. So Microchip is investing, not only supported us, but we're investing further in RISC-v.
So when you send a processor into space, we talked about the FPGAs being flash-based, so they can't easily lose their state. How does that work with a processor which is more complex, and how do you how do you protect those in space from radiation and things like that?
There's a lot of ways to skin that cat as well. So one way people skin that cat is buy 3 processors and hook them up together on a board and then vote the outputs. That's a brute force way of doing it, but it's done. Then there's people who there's parts of this project that don't have those constraints, and so if an error happens in a certain payload, they just things aren't working, but it doesn't fundamentally corrupt anything, and it'll start working again, or they'll hit a soft reset and just get going again. Some applications can tolerate that. So there's the worst is put 3 of them on there. The others do nothing and just deal with the reboot. Then there's a kind of whole spectrum of stuff in between, so one is you can do with middleware that figures out all this stuff for you and gracefully deals with these problems at the software level when an error happens. But you can there's something called rad hard by design. So where you basically use the existing process, you don't change the process technology, but you change the library or the way you design things to make it robust against these type of failures.
I see.
So one way of rad hard by design is just what I talked about with 3 chips on the outside. You can do that, that triplication internally. But then there's also people who make ASIC libraries, standard cell libraries that are resilient. So those libraries are will be bigger and not as compact necessarily as the standard library, because there is basically triplication going on of some sort, redundancy going on at the flip-flop level. So that's one effect that's called single event upsets, where you're worrying about a flip-flop maintaining its state, basically. So rad hard by there's rad hard, and that's something that applications different depending on your application use case. You may need different levels of protection. Another thing called single event effect, called single event latch up, where heavy ion usually it hits the part and it latches up, and it can be destructive, where the chip starts consuming all kinds of current and burns out and is not recoverable. So techniques are needed to deal with the single event latch up, and so those usually involve things like guard rings and other things that add some cost, so it have to be consciously put into the chip. With the processor itself, main thing is upsets with the with the logic, with the pipeline, and how you deal with that. And you can harden it by design. You can ignore it and just figure it out. Of course, processors originally didn't have ECC in the memories. Now they all do, because the ECC is a terrestrial problem. It's not just a problem, but that ECC, the error correction coding on all the memories is done for everything on terrestrial, and that solves a lot of what a processor sees So the ECC is kind of there, but then you can go further and harden the actual, all the logic in the processor.
Yeah, that's interesting. Yeah, I recently there was a YouTube show where Linus Torvalds got a new computer built, and one of his requirements was he wanted ECC RAM in his computer for reliability. So I just thought that was interesting. Most of us we don't really care too much about that, but yeah, if you want reliability, that's the type of things you need to do. So
yeah, so I think so again on my slide, I think all these things, reliability, security, low power. It's the whole. The data center is one thing, but then there's just tons of device needing more and more compute out at the edge, and certainly in a lot of those markets, like cars are basically edge devices now.
Yeah.
You're gonna need the reliability.
yeah.
But then security, everything, all those devices can be hacked, because they're exposed. There's no data centers. They're hidden behind, physically hidden behind guns. We call them guns, guards, and gates. But the physical attacks are a thing that we're good at defending against with our technology.
Mm-hmm. So
that security, I just want to just do a side check. There's, like I said, a dozen reasons why I was attracted to RISC-v, and one of them was security. We've been on the vanguard of FPGA security. We've had, and we're finding out, we know about problems before our customers do, and we knew that there was a minefield of security problems built into all the processors out there. So I knew, I saw RISC-v as a way to is the right platform to start do security right for the whole processor industry. And I couldn't get. I was trying to say, we need a RISC-v security committee. People knew about security, but they weren't that. I wasn't getting through to the board of directors now. And then, Spectre and Meltdown hit. I don't know if you remember those two things. And Dave Patterson said, "Oh, whoa, wow! Security is real important." So he had a Turing talk, which he won the Turing Award about that same time with John Hennessy, and he had the golden age of computer architecture. And it was, one of them was open instruction sets, hardware, software co-design. There was lower cost to design, and then he added, security. And I think I helped him. I kind of tuned his filter, so when something really happened, he latched in that security was something that was going to be important to compute. And RISC-v, lets you solve those problems. Kind of a non-intuitive thing is if you have an ecosystem where everyone's making a different version of the microarchitecture, if something happens, you're not going to it's not a monoculture. It's going to take out everything. It's so it's got these counterintuitive security aspects of just RISC-v being open lets you avoid the monoculture, and just one of the aspects of RISC-v that are interesting from a security point of view. Anyways, sorry about that.
I think that's really a good point, because I think the compute has gotten into a lot of places now than before, right? So you think, and security as an afterthought is gonna be quite precarious. I mean, in that situation, we'll end up in this, attacks that you talked about, and side channel and all that sort of stuff that happened in the past, recent past. So, so certainly, I think more and more, critical kind of software is kind of needed on this critical business operations, beyond what it used to be. I think it's kind of getting to that point where it should be, a basic requirement, that it's not something you bolt on afterwards, but it's kind of, in the design as a first principle.
Yep. The tricky thing is to get people to pay for that, though. No one wants to pay for it, but everyone needs it now.
Right.
And they, yeah.
It's like an insurance policy, hard to sell.
Yeah. I mean, we do. I mean, we sell a lot to people who's living in the aerospace and defense markets, right. And some of these others. So there's other companies, anything with critical infrastructure, people are doing the communications infrastructure for the whole world. They know that there's a security problem. So we're not just in defense and space market, but for our security, there's people who pay for us because of they're involved in the critical infrastructure, and they're very familiar with nation states coming after their stuff.
Yeah.
We're in the vanguard in that type of product.
Yeah. So you talk about processors, and we always have this discussion around microprocessors versus microcontrollers. Microcontrollers being simpler, in model and design. How do you see the landscape change in your recent decades? Like everything moving to CPU kind of compute units, or MPUs.
So I think the market data bears that out. I told you we wanted the real time and Linux,
right,
for a long time, and we kind of made that happen. But other people kind of solved that problem by putting heterogeneous things on their chip with a A-class processor and some R5s on there.
Yeah,
we didn't want to do it that way. So, I mean, it wasn't my observation, but Linux became everything, right? The people building systems, it's just much easier for them to work at the Linux level, and they pull out whatever packages they need and work there to get that stuff done. And the costs have come way down for that type of that type of product. So the pressures of people and companies trying to build new hardware, they don't have time necessarily they don't want to spend that much time on squeezing the most out of the hardware that they have. It's much more valuable to them to be able to just use an operating system like Linux to get their product out. So Linux is everywhere.
Yeah.
So that's the. So my short answer to your question is I see that trend happening, and it's going to reverse. Certainly not in terms of so it's a steady. It's a good business. People need the business. Things get bigger, they'll grow more, but the exponential growth is going to come from something that's an NPU type of thing.
Yeah, that's interesting. Yeah, I spent a little bit of time, or a fair amount of time, working with Zephyr in the last year, and it can do a lot of more advanced things now, like HTTP servers and a lot of communication stacks. But I agree, it is a lot more difficult to get something done in Zephyr than Linux. So if you have the opportunity to use a Linux capable system, it's gonna probably shorten your development time and give you more runway to expand the system later.
we're actually it's interesting though. So I know, we're definitely, pretty big investment here in Zephyr.
Oh, good.
So we're members of Zephyr, and I remember seeing a slide. I forget who was. A lot of momentum in Zephyr for sure, compared to other pre-existing MMU-less OSs, let's say. So Zephyr's making good progress. So we're investing in it.
Yeah. So are you targeting Zephyr on the PolarFire, or would that be more Microchip's MPU?
Well, so PolarFire SoC, we've got Zephyr. We support Zephyr. We have guys in our FPGA group participating in Zephyr working groups, but it's also in the other groups in Microchip are all for our controller line are also investing in Zephyr.
Good. Yeah, it's a wise thing, I feel. So
yeah, I think Zephyr is to MCUs what Linux was to the MPUs. I mean, it is now. People won't write RTOSes anymore, right? So they'll basically there is one, they'll keep using that, probably adopting it, as their use cases come by.
Yeah, I remember. I saw the adoption curve. It's been a while since I've checked it, but I said, it's an old, look obvious that Zephyr. I think it was a curve of measuring GitHub contributions to these things.
Yeah.
Zephyr was way higher than all the other ones. So it was obvious that Zephyr seemed like it was a living, thriving organism.
Yeah. I think some of their decision choices, in terms of infrastructure, how to engage with developer community and their user community has been quite good. And, I'm always amazed, because I guess that traditional RTOS developers use Windows or some sort of very different kind of development machines. And then, taking them from there and Linuxy experience, development environments, and walking them all over to this new GitHub model of contribution. It's quite a feat that they have achieved.
Yeah. So I'll give an unsolicited shout out. So I know, a company called Ant Micro.
Yeah.
Yeah. So they're big Zephyr proponents, but they're also early on to RISC-v, an early development partner for us with our processor emulations. But they believe in all that stuff you talk about, GitHub doing stuff in open, and I think they're an important contributor to the Zephyr at this point.
Yeah. One thing that really impresses me with Zephyr is they've convinced all the MCU vendors and whoever else to bring their HALs to the Zephyr community, and everything's integrated there. And that's kind of different than what people have traditionally done, where you kind of throw an RTOS over the wall and then the MPU vendor integrates it into their IDE. It's kind of reversing the model, and I feel that's one of the big differences between Zephyr and the other RTOS players, and really is what enabled the cross-platform features of Zephyr that work so well.
Yeah, I don't want to get too far over my skis here. I don't know. I'm not a developer at all, but I'm kind of interested in how things take off, how things win ultimately, and so that sounds sounds kind of compelling to me, and definitely. But I wasn't aware of what you just mentioned.
Yeah. So let's talk about some of your SBCs. I know that Beagle 5 Fire had, I think, the FPGA, the PolarFire FPGA, I believe, in there. So what are some of the programming models, or how you see it being used. And so if you could talk to that a little bit, that would be really awesome.
Okay. Let's see. So FPGAs companies, when you make an FPGA, you have to offer them with development boards.
Mhm.
It comes off, but so we've got development boards with our PolarFire FPGAs, and then PolarFire SoC is the one with the RISC-v components on it.
Mhm.
And I'm trying to remember the names of them. One of them is a development board, PolarFire SoC, for what we call the SEV market, Smart Embedded Vision. So it's that board. It's called the SEV kit, PolarFire SoC SEV kit. Has everything you need to plug in cameras, run displays, and the IDE to program the RISC-Vs in that kit. So that's the SEV kit, which was a little bit better prepared. So the Beagle Fire's interesting. So this is kind of another thing I'm interested in and want to kind of make more progress in, but just to exploit open source world. So the guys at Beagle Foundation, they extracted themselves from TI and saw a future for RISC-V and came to us and said, we want to make a RISC-V, Beagle 5 with your PolarFire SoC, and they got another ones out there. But what's different about ours is it does have the FPGA next to it. So now you've got they have to support a new programming model that their ecosystem hasn't had to do before. So how do you program that FPGA that's connected to it? So that I think probably better able to talk about that in the future. But apparently, just talking just this week, the guy in a company who's kind of the engineering liaison with Beagle, and he says that there's someone in the open source community that's doing a lot there that lets you basically almost program the device at the device tree level. So you build an IP and then just put it in the device tree, and then the whole software works. So I think there's some innovation going on with the Beagle Fire and how to an FPGA, how to how an SoC FPGA should work. That the open source community is creating. And then that's starting to the dream there is get someone open source famous like Beagle to use our hardware, use RISC-V, and then do something innovative on how to use an SoC FPGA. So I would say that's in progress. So that's a good way to get our hardware. And be, I think, again, you want to be a part of something that's alive, that's interesting, that has room to innovate. I think Beagle is a good choice. And so then the SEV kit is the one that, again, we sell the most of, and then we have the names escape me. Our introductory board, what's it called? The Icicle kit.
Icicle kit,
is there the first board that we had introduced the RISC-V SoC on. So more to come.
Very cool. I also saw some of your PIC 64, and that you, at the RISC-V conference recently. So it looked very interesting. What are the use cases for that that you're targeting with the SBCs, or that kind of form factor?
So again, the use cases are the things. I mean, so it's use cases. SoC FPGAs, first of all, are becoming, most FPGAs today now are becoming SoC FPGAs, FPGA with a processor and an FPGA next. And a couple of reasons for that. Some people don't want the processor and use the SoC FPGA as the main processor in the system. Others are, if you take some logic, it's some of it's better to be in the done in software.
Yeah.
If you have fun, it's better to be partitioned between software and hardware. So an example of a use case for SoC FPGA would be, you want to do some encryption or inline encryption, or you need to interface to video interface or inputs or sensors. AI is a application we've invested in. We have a product called Vector Blocks, which is implemented in the FPGA fabric to do. It's called an FPGA overlay, where you program something into the FPGA, but that thing itself is then programmable. So you can you don't just program the FPGA one time. You don't have to run place and route every time. You can basically, if someone gets a new model or new coefficients, it's easy just to software, do your inferencing, without having to, do a complete replace and route of your FPGA design.
Yeah, that's interesting use case. Yeah, I didn't think in that way, but pretty interesting. Very cool. So, what are some of technologies that interest you nowadays or in future in 2026?
So I've always been interested in the space market, I would say, and it's we've always been involved. Since I've been here, like I said, we've been to Pluto, we've been to we're now beyond Pluto. So the space is cool, but for my I've been doing. I always thought that the high ground is actually where the market ultimately is going to grow, and it's I've my keynote I've done like 3 or 4 RISC-v based space keynotes in the last year. Did one at the RISC-v and Space Conference, did one at the Space Computing Conference, and then did one at the RISC-v Summit. And so I did 3 of those, and I had a picture, and I was walking through Austin Airport once, probably end of last year. I took a picture. Dell was running an ad saying, Dell now on the moon, and to me, and then I took that picture and I said the slide, every technology company is going to have a space strategy. And then I started giving examples in my talks of, so we went to Polar Fire SoC has actually been on the space station already. The company called Space Built. And then Space Built also built hardware for us. So we actually went to the moon. It was one of those landers that landed on its side. But we went to the moon on a company. It's going to, thinks they have their tagline that said the moon is so perfect for storage that if it wasn't there, we'd have to build it. So they have plans for building data storage, disaster recovery, that type of thing on the moon. And it's a company called StarCloud. They have a white paper on elaborate plans for training networks in space. So anyways, I was going around saying, watch for it, watch for this, watch for this. As soon as my last one, RISC-v Summit, Elon Musk said, we're going to build data centers in space. CEO of Google, we're going to build data centers in space. So it went, someone said it crossed into the Overton window. So I was talking about it. And so I'll take credit for making it happen. So anyways, the space market, everything that's being done on the Earth is going to be, everyone, any company is going to need a space strategy. And so it's going to be, so from the servers to the, the edge type devices, there'll be tons of sensors out there. More compute out there, tons more sensors in space, but they'll have to, send stuff down to the Earth from terrestrial. So it's going to become, space can become a part of the, the world compute ecosystem. It used to be data centers, transport, edge, and now there's going to be, space, data centers, transport, edge, and, space will be orbit, and it's going to be moon, it's going to be Mars, and, Microchip, we have we won the contract with NASA. We won with the RISC-v, so RISC-v is proposed is well positioned to take advantage of this. Microchip is well positioned to take advantage of it, and it's cool. So if you want to do something cool stuff, you definitely want to come to Microchip.
I think I'm pretty sure you heard of the Space Grade Linux. So there's like this initiative to get Linux to be.
Well, we got the same people were contributing to the. You probably run into them, but the same people contributing to Zephyr also were contributing to the Space Grade Linux as well.
Yeah, that's awesome. Like my tangent through Yocto in there and other stuff. So, but I thought that's pretty interesting project. In terms of validating, what you were just saying about space strategy, and of course the announcements or the tweets from Sundar Pichai and then Elon Musk, that kind of also validates that they're pretty serious about it. I guess then it's just not a space talk.
I'm declaring my prediction there is a victory. And I literally said at the RISC-v Summit, you may think I'm crazy, but they're going to be data centers in space, this, and all of a sudden, it's like literally a week later, it started, everyone started saying these things. Google publishing the white paper. So we got, so there's a part of, RISE, the RISC-v software ecosystem organization. We got, people from NASA, saying, okay, we need this, we need that. For, so I'll say one more thing about RISC-v in a second. I'll come back to that. But anyway, so RISE is now working on projects that, if you want to work on something cool in RISC-v, chances are it's going to go in space. But there was, I was really worried. We bet on RISC-v for NASA. We said, NASA, we can build you this hardware, and I knew the hardware was going to be there, but I was, that's someone's going to really be making sure, checking, making sure the software works. And I was kind of nervous, and I was like, talk to the program people for HPSC, and they said, stuff is working. So everything they needed is working, not necessarily as well as they wanted, but RISC-v, software works, and that's, hats off to people like you, Ken. I mean, that's what
Yeah.
no one necessarily understands, that this is a huge thing. And
Yeah.
all it started with just people like you, just wanting to work on RISC-v, and had my back, and I was, and so makes me look good that someone at NASA's job is to make this thing go, says it's all there, it just needs to get.
Yeah.
That was vindicated. That was my keynote. That was one of my points. Was the NASA said the software is all there, but the guy just before me at the RISC-v summit was a guy at Google talking about RISC-v and the Google data centers. And he said the thing: the software's there. It's not as good as we want, but the RISC-v software is there. Yeah. So that should definitely be a message for your, takeaway from your listeners. RISC-v is there. RISC-v is cool. Microchip is in the middle of all this stuff. Space is cool. So.
Yeah, that's awesome. Actually, I think, just to add to what you just said, one of the things that, being involved in open source, one thing I realized is that when RISC-v came along, that, some of the past mistakes, not to repeat, are upstream first strategy. Even though the hardware doesn't exist, the software shouldn't be sitting on the side. So, just push upstream for every component, right? So whether it is the Linux, whether it is the libraries or applications, just make it upstream, right? So upstream first strategy. I think that's different than other architectures, So it took them a long time. They collected patches and patches and patches on the side. And, that collectively causes quite a bit of problem in basically, making that go, because you build upon each other, right? So essentially, if you're having patches on to kernel, 100 patches sitting somewhere, first of all, I need to know about them. And then I need to get them onto my tree and then build on top. So, it adds friction. And so, for a longer time, I mean, the whole software thing, in Linux, at least I can say is there was no hardware, but there was emulators in QEMU. And 95% of Debian packages were ported. And and somebody said, I was kind of talking to someone, I said, now we just need hardware.
Talking to, so everything happened RISC-v, kind of faster than anyone was predicting, except maybe me. but the hardware is definitely it's taken longer. So if you ask Krista Sanovich, what the software guys really need to really make it go quickly is the high performance hardware out there, and it's starting to get out there. So that'll be the final piece of the puzzle, hopefully. 23A, I think, is a big aspect part of it as well.
So you mentioned about your new chip. Is it going to be RVA 23 with vectorization and stuff?
So the HPSC is not. So we're going to at least there'll be future versions of HPSC. But it was we bit the bullet before the. But it's got vectorization, but it's not fully compliant to RV23A. I always remember RDA 23. I always get that. I can't handle all the acronyms.
Pretty cool.
So this is kind of a dangerous to do. It's a lawyer. Don't ask a question you don't know the answer to. But so how do you just quickly, how do you think it's going for RISC-v?
I think it's going well. At least, I look at the software side of things, the aspects of stack are being optimized now. I can see the key pieces of software are being optimized for, like FFmpeg or something. And then UDC patches for, the products to implement, the the pieces in assembly or in inline assembly to use vectorizer and that sort of stuff, which means it's moving to the next level where, hey, let's get it working, to now, let's get it to the next stage, which is optimized workload. So
that's the same message basically. It's stuff works, and that's the first hurdle. And now, the silicon's showing up, the applications are showing up, and so I think the focus, I expect a lot of progress in the optimizations, getting things going.
Yeah, and I think from tooling perspective, I mean, there is things to be desired in compilers and all. If you compare, the code generation with respect to more mature architectures in terms of x86 ARM, maybe there are a few glitches, few things to be had, but it's just the next step in my mind that you from optimizing it. So 26, the porting part is over. All the foundation work that you did, that's probably over. By now, it's more now that's the rough edges. That's kind of smoothing them out. That's what is going to happen now, I think, more and more. And RISC is helping with that quite a lot.
Yep.
So
cool.
So any reading recommendations, other podcasts other than this, or any YouTube videos, or anything that you like to talk about? Or
sure. I'm trying to remember something in RISC-v. I mean, he's not producing the at the same rate he was, but Lex Friedman. I mean, started consuming. He's usually started was just interviewing all these guys who created the whole computing, really, in a sense. So it was Dave Patterson, Jim Keller, he's had on many times. So that was actually my first when I started. I didn't use YouTube hardly at all until someone pointed me out to him. So I'm trying to think who tech that I listen to a lot now. A lot of my YouTube bandwidth is going into other areas. I like listening to history podcasts, and for some reason I'm fascinated by the Stalin era. Stalin podcast that's about Stalin, and books. I'm a nonfiction guy. There's some books have either helped me think about things, reinforce things, way to think about. So I mentioned one already is Innovator's Dilemma, Clayton Christensen. That's, I think, an important book for anyone. So that's the whole idea of a disruptive technology starts out as something that's not nearly as good as the incumbent technology, but meets some need, and then eventually becomes the incumbent technology. And RISC-v is obviously, and usually it's not a technical thing, it's like a business model or a form factor. So RISC-v is a new business model for processors, and that's but when that happens, it's hard to predict who the winners are going to be when something disruptive. But anyways, the Clayton Christensen book, Innovator's Dilemma. And I read all of Nassim Taleb's books. He wrote this book called The Black Swan, Skin in the Game, Fooled by Randomness, and what's the other one? Infragility. What's that thing called? Oh, damn it. But anyways, Nassim has definitely a different way of thinking about things that are counterintuitive, that kind of help me realize situations that are going on. I'm trying to remember, he didn't have a name for it, but a project where when they say it's going to be done in a week, and then a week later they say it's going to be done in 2 weeks, and then 2 weeks later they say it's going to be done in 4 weeks, and
time stretches, the work stretches to time. And
you think probably a lot of people have been involved in projects like that. And the kind of root cause of that is, in a lot of cases, unknown unknowns. Where people just don't know what they don't know. And so I always, when I'm running projects, I always try to make, trying to find it. I'm trying to figure out what we don't know, and figure that out as quickly as possible. They're always out there, but so, anyways, all the Taleb books give me a good view on thinking differently to use Apple's marketing slogan.
Very good. Yeah, I think it's really cool recommendations right there. So any advice for the young people out there who are kind of trying to get or are interested in the tech space specifically?
Well, it probably seems AI obviously is I mean, if I'm young there, got to be worried about, AI is like, oh, that's a big uncertainty, but you definitely have to, kind of embrace it, I guess. Don't be afraid of it. Dive in, and that definitely doesn't mean getting a job in AI necessarily, but learn to use it in the right way. I think that's going on. My general advice, a lot of been in the same place for a lot of years, so there's a lot of stuff I know but don't do, but it's all strategy is not. And this is a Taleb thing, is not being some smart guy, figure out we're going to do this, and this is all going to work out. Strategy is creating options for yourself, and so you always want to create optionality. And so when you figure out that one of those options is the one to bet on, then you bet on it. But you don't want to get. As soon as you get locked into one track, you're in a path to probably ultimate failure. So creating optionality is what if you're a young person, that's what you want to do with your career. So you want to, one way to create optionality, which is I'm bad at, is meet people, right? Be out there, go to conferences, and be out there. So one thing for the future is you can't predict the future. You can. People say make your own luck. The way you make your own luck is create the options, and so you and then obviously go down the path that is seems like the best at time. But even if you go down that path, be ready to move. So if you have a company or individual level, I think that advice applies, and create the options. So a company that can create optionality for itself, or a person create options for themselves, you're in a robust and Nassim would call it an anti-fragile position. You always embrace it. Things blow up, that's good for you. That's energy you feed off of, versus fragile, where something happens and you die. So stay anti-fragile is my advice to young people.
Yeah, it's very interesting. Someone else I was talking to recently talked about optionality, and so it's a term I'm not real familiar with. So I appreciate hearing your advice on that.
Are you a young person, may I ask? Advice applies to all.
Yeah, I think it's.
I believe I feel like I've been in the same place forever, but I'm always. I still feel like I'm hitting my peak. I think there's a lot of things that can happen.
Yeah,
that's just by the opportunity I have, and it's exciting.
Yeah.
Well, that's appreciate all you shared today. I've definitely learned a lot about the RISC-v and FPGA fields.
Yep.
So
Yeah, well, again, like I said, hopefully I met your expectations. Interesting conversation. I'm happy to talk at length about any of these things. So I hope anything I can do to help get listenership, and hope is a good podcast for you.
Yeah. Well, we definitely appreciate all you've shared, and we appreciate our listeners. And if you have any comments or feedback, please let us know at the Tempter community or any of the other places we hang out. So, thanks again, Ted.
Thanks, Ted.
Okay, thanks. All right, thank you, guys.